Okay, so thank you very much for joining us for the first RTNP seminar in the fall 2020 semester. So today we are happy to have Milen Yakimov from Louisiana State University, and he will tell us about the Poisson geometry of large quantum groups.
Thank you, Simeon. I want to start by thanking Kole, Vera, and Simeon for inviting me to give this talk. I'm very excited about this. I hope very much that the situation in Berkeley will get much better in the following days. It's really terrible to see all these fires all over Western US. And this is a joint talk with Nicolas, Andruskiewitsch, and Ivan Angiono from Universitat Nacional de Cordoba. And I want to say that I learned a great deal of math from them. I'm coming outside the area of Nichols algebras. One of the things that I want to do in this talk is advertise this field of Nichols algebras. It's a beautiful, very general tool for dealing with algebras that have set relations as definitions. So it's really like a sort of powerful technology. I want to start with a few general words about the influential work of the Concini-Kac-Procesi from the 1990s. They wrote the sequence of papers in which they defined big quantum groups at roots of unity, and they found very strong tools for studying the irreducible representations using Poisson geometry. Let me be more concrete now. So the starting data is G, any complex simple Lie algebra. Epsilon is a primitive nth root of unity, where the order is odd and is co-prime to 3 in the case of G2. As an algebra, the big quantum group U epsilon of G is a Hopf algebra, which has exactly the same generators as the traditional UQ of G, and relations that are obtained by replacing the indeterminate Q with the root of unity epsilon. So we're going to denote the generators by Ki raised to power plus minus 1, Ei and Fi. The rank of the algebra is n. And we're having the standard relations. For instance, for the big quantum SL2, we have the usual 3 relations that are on the bottom of the slide. The punchline of the work of the Concini-Kac-Procesi is that they constructed a big central subalgebra. It's a special central subalgebra. It's generated by the nth powers of the root vectors F, as well as by the nth powers of the Cartan generators K1 raised to power plus minus 1, and so on, Kn raised to power plus minus 1, again, n powers of those. This algebra is big in the sense that the big quantum group is finitely generated and free module over this subalgebra. And a warning, it is far from the full center of the big quantum group, because the full center of the big quantum group contains the Casimirs, and this algebra does not contain the Casimirs. It's also a Hopf subalgebra, unlike the full center, which is not a Hopf subalgebra. This particular fact that it's a Hopf subalgebra played a key role in a later work by De Concini-Procesi, Kola, and Mark Rosso. The small quantum group of Lustig is a very special algebra, finite dimensional Hopf algebra, to be obtained from the big quantum group in a very special manner. If you take the maximal ideal of the center that's generated by the n powers of the root vectors E beta, F beta, and Ki raised to power n, so this is a maximal ideal of the center. The spectrum of the center is, I'm sorry, it's not a good idea to operate with the pointer, so I should completely avoid touching the pointer. So if you take this maximal ideal of this central subalgebra and you quotient the algebra, the big quantum group, by the ideal generated by this maximal ideal, you get precisely the small quantum group of Borel, of Lustig. And furthermore, the punchline of the Concini-Kac-Procesi's work is that you actually get a bundle of algebras over the spectrum of the center, where the fibers are parameterized by all maximal ideals of this center. And for different maximal ideals, you get different finite dimensional algebras. These are finite dimensional algebras that are completely different from each other in general. However, you can use deformation theory to study the representation theory of one of them, like the small quantum group of Lustig, using the generic fibers of this bundle over the spectrum of the center, of the special centers of algebra. So the story here is that the Lustig small quantum group is just one fiber of this bundle of algebras. This kind of situation has been studied in great detail in non-commutative algebra. So it's been since the 50s, 60s, and 70s, there have been a lot of works in this direction. And the general picture is people like Procesi, Artin, Kaplansky, Posner all have major contributions to this. And the general picture is that we have a complex algebra and a central subalgebra Z, such that this non-commutative algebra is a finitely generated module over the central subalgebra. These are special cases of what people call PI algebras. We denote by Ir A the set of irreducible representations of the algebra A. And it's a very easy exercise that all of these irreducible representations will have to be finite dimensional. Now we can apply Schur's lemma in order to get that the center Z is going to act by a character on every irreducible representation of the algebra A. So in other words, we get a vibration map from the irreducible representations of the algebra A to the maximum spectrum of this special center of algebra Z, where a representation V goes to the maximal ideal of Z that kills the representation V, or in other words, this is the annihilation ideal of V inside the central algebra Z. So now we have this geometric picture where we have this vibration psi, and over each point M, which is a maximal ideal of Z, we have a fiber. But now the key point is that each such fiber has a very nice description. The fiber over a maximal ideal M by definition consists of irreducible representations that are killed by this maximal ideal M. But algebraically, this means that these are irreducible representations of the factor algebras A mod MA, and all of these algebras A mod MA are finite dimensional modules. So over each point M, we see precisely the irreducible representations of this finite dimensional algebra A mod MA. In some situations, A could be a free Z module. In some situations, it will not be a free Z module. But when A is a free Z module, these algebras A mod MA, they actually form a bundle. In general, they just form a sheaf. But in this freeness situation, they're going to form a bundle, and the fiber of these irreducible representations, the fiber of psi, is precisely going to be the set of irreducible representations of this finite dimensional algebra A. So in general, this freeness is not a needed ingredient, and in many situations, we have central subalgebra Z for which A is not a free module over Z. However, A is still finitely generated over Z. So from the previous slide, we see that the big quantum groups fit inside this picture, but there are lots of algebras in mathematics that fit into this picture. For instance, all the activities that are very hot at the moment about modular representations of Lie algebras in prime characteristic fits into this picture because one can consider the non-restricted universal enveloping algebra, and then the restricted universal enveloping algebra is just one of these fibers of a vector bundle like this one, with the only difference is that that is in positive characteristic, and the picture that we're going to see today is in characteristic 0. So people like Procesi have been thinking a lot, how could they understand the behavior of the fibers when M varies as a point of the maximum spectrum of Z. And in that work of the Concini-Kac and Procesi, they came up with a powerful notion, is the notion of a Poisson. So Poisson order is just like before, an algebra A with a central subalgebra Z, with the property that A is a finitely generated module over Z. And we're saying that a pair like this AZ is a Poisson order if one, Z is equipped with the structure of Poisson algebra, so it on its own is a Poisson algebra. And two, there is a linear map. This is not a homomorphism, just a linear map from this Poisson algebra Z to the algebra of derivations of the algebra A, such that for each Z, partial Z extends the corresponding Hamiltonian derivation of the Poisson algebra. So really this second part is the punchline of the construction that links Poisson geometry to the representation theorem. Because we're saying that whenever we have a Hamiltonian derivation of our Poisson algebra, that Hamiltonian derivation sees the Poisson geometry, we can extend it to a derivation of our non-commutative algebra A. And in a sense, these derivations of the non-commutative algebra A, they see precisely the irreducible representations of A. So this second part of the definition is precisely the internal link between Poisson geometry of the central subalgebra and the representation theory of the algebra A. And a theorem that was proved in a very special case, by the Concini-Kac-Procesi, not very special case, and later Brown and Gordon gave a proof in full generality, is the following. If you have one of these Poisson orders, and if you pick up 2 points that are in the same symplectic leaves of the spectrum of Z, and then you look at the corresponding central quotients, remember these are the algebras that govern the fibers of Z. The algebras are actually going to be plane isomorphic to each other. So it's a very special case. We get that we have a bijection between the corresponding fibers of C. Like if we have one fiber and another, we have bijection between the points that preserves the dimensions of the irreducible representations. But the really remarkable part is not only the representations are the same, but the actual finite dimensional algebras are the same. In many situations, this theorem is so powerful that it says that if you look at these central quotients, A mod MA, there are only finitely many isomorphism classes of such central quotients. So in a sense, you started with an infinite problem to understand the representations of A mod MA for infinitely many M's, and all of a sudden you got just finitely many. So this is the theorem. And now back to Poisson orders, there's a very general way of obtaining Poisson orders by a very simple construction of specialization. If we start, so we say that the algebra A is an algebra, is a specialization of the algebra R. If we can find a non-zero divisor, I forgot to say non-zero central element H in R. So it shouldn't be a zero divisor and it should be a central element of H, such that A is the central quotient of R by this element H. So then we say that the algebra A is a specialization of the algebra R. Whenever we have this situation, the pair A and center of A has a canonical structure of Poisson order. And it's defined in the most trivial way possible. If we denote the projection from R to the quotient R mod HR, I have a misprint there. The quotient R mod HR is isomorphic to A. I'm missing the A after the isomorphism. And we pick any linear section iota from A to R. The algebra A and the algebras R are very different. For such a section iota will never be a homomorphism of algebras. It's just a plain linear section. Then the Poisson structure on Z is the bracket between Z1 and Z2 is we apply iota to both of them. To get something in R, we take the commutator that's automatically divisible by H. We divide it, we project it back, and that's our Poisson structure. The partial map is given by pretty much exactly the same formula. So that's the general way of obtaining Poisson orders. And in our applications, this central element H is always going to be Q minus some complex number. the algebra R will not be just an algebra over C. It will be an algebra over Laurent polynomials in Q that's a little bit localized. And definitely in this situation, Q minus epsilon is going to be a central element because the algebra is an algebra, the algebra R is an algebra over Laurent polynomials. The main point here, though, is that the full center of an algebra A is in pretty much all cases a singular algebra. So we don't want to do Poisson geometry with the spectrum of this singular Poisson algebra. So we always need to construct a large, smooth Poisson subalgebra Z. And if Z is a Poisson subalgebra of the center, then just by restriction, the pair AZ is going to be a Poisson order. So the main difficulty all the time is to prove that if you construct a subalgebra Z of this center, that it's actually a Poisson subalgebra, and to describe it, what exactly is this Poisson subalgebra? Those are always the hard parts because you have to use the definition, but then into this definition goes to like lots of details. So you can't really do a direct argument. Here is my Z, it's obviously a Poisson subalgebra. So now going back to the Concini-Kac and Procesi work, the key points that they did in their work is the following. So first they proved that the big quantum groups are specializations. And then they proved that as a consequence, the big quantum groups and the full center of the big quantum group is automatically going to be a Poisson order. However, the center of this big quantum group is extremely complicated and singular. So they wanted to avoid the singularity, and they used the central subalgebra Z epsilon of G that appeared on the previous slides. So they proved that that Z epsilon of G is a Poisson subalgebra of the full center. And finally, as a third part, they proved that the Z epsilon of G is isomorphic to the coordinate ring of the dual Poisson algebraic group of a simple algebraic group with a standard Poisson structure. We will see a little bit of this later in the talk. And as a consequence, they obtain the invariance of the central quotients of the big quantum group along conjugacy classes of this group G. So here are the goals of the talk.
Sorry, may I ask some philosophical question about what was on the previous slide?
Absolutely.
So you were explaining that the representation theory of this quantum groups of roots of unity is very much dependent on the Poisson structure of the center.
Yeah.
But of course, the same. I mean, sort of the same is true about just representation theory of just quantum group with generic Q is also very much dependent on the Poisson structure of the G dual, the dual Poisson B group. That's okay. That we can probably just say, well, if it's true for roots of unity, that's probably true in general. But then sort of the same is true, of course, about representation theory of just usual universal enveloping and the Poisson structure of the G dual with the trivial Poisson structure. And there you don't see any big center. So somehow, is it a related, well?
Completely, it's a great question. It's completely in the direction of what's called the orbit method program of Kirillov and Kostan. And one thing that was found is that when you look at the universal enveloping algebra of a nilpotently algebra or nilpotent group, there is a very good way of constructing using geometric quantization, constructing the irreducible representation, so the unitary dual, using the Poisson geometry of the nilpotently algebra. However, the moment you move into semi-simple algebras, this statement that the irreducible representations of a semi-simple algebra in somehow in bijection with cojoint orbits is very much still in developments. People try to do all kinds of things that are more and more interesting. They look at some local systems on cojoint orbits, or all such kind of things. This was like a very big development in geometric quantization, but still this philosophy that there everything is really in bijection is still, to me, is somehow not well justified. So the beauty of this concrete construction of Poisson orders is that the moment you're sort of in characteristic P, or at roots of unity where you have a large center, things are actually a lot more concrete in terms of relation between Poisson geometry and irreducible representations.
But this is exactly my question. So I understand about the orbit method, but somehow it's not that you can see the, so in the case when your Poisson vector is just zero on G and you take the dual, you take the G dual as a Lie algebra, right? It's not that you see this dual Lie algebra as a center of usually universal enveloping at any parameter H or at characteristic P. So you kind of see it as the center of anything, right? The Lie algebra G dual, or can you? Is there some formulation which you can?
From my perspective, there are many people who try to prove results about reducing representations from general situation to the PI situation. For instance, Mathieu has a number of results about representations from characteristic 0 proved by reducing to characteristic P, but I don't know of a general method that actually links one set of irreducible representations to the other.
Thank you.
So here are the goals of the talk. So in the late 1990s, Andruskiewitsch and Schneider initiated what in my view is a very powerful program for classifying pointed Hopf algebras. Just to say very briefly, I don't want to define pointed Hopf algebras in some technical terms, but I want to say that every Hopf algebra that's generated by group-like elements and skew primitive elements is automatically pointed Hopf algebra. And in a way, this class of pointed Hopf algebras contains all important Hopf algebras that have been defined to moment. So I want to provide a sort of intuitive introduction to this program, to the notions in this program, and do some sort of advertisement for this program. So in that program, there is a very large family of infinite dimensional Hopf algebras. And as very special cases of this family of infinite dimensional Hopf algebras, we get all multi-parameter, even big quantum groups at roots of unity, all big quantum supergroups of roots of unity. And we even have exceptional families that can be thought of as quantizations at roots of unities of some finite dimensional simple Lie algebras in prime characteristic. For instance, there is a 34-dimensional Lie algebra of Katz and Weisfeiler defined in the early 70s, and it has a quantization that is a certain Hopf algebra defined with respect to roots of unity, with respect to some roots of unity. So in all this, we're going to describe extensions of the Concini-Kac-Procesi results to all of these algebras. In particular, we'll have extensions to all quantum supergroups at roots of unity, big quantum supergroups. And here I want to say that the Kac-Procesi rely a lot on concrete calculations of Poisson brackets and reductions to rank 2 cases. Rank 2 because all quantum set relations for usual quantum groups contain only 2 generators. However, if you look at the kinds of quantum set relations for quantum supergroups in these exceptional families, there are 13 additional kinds of set relations, and some of them have 3 and 4 generators. And doing exactly the same thing that the Concini-Kac-Procesi did, reduce this to all set relations, is simply impossible because you have so many different kinds of set relation. And instead of that, I will sketch this a little bit by using some methods where we use perfect pairings between restricted and non-restricted integral forms. And we avoid any ad hoc calculations with Poisson brackets. And with respect to these pairings between restricted and non-restricted integral forms, we can directly describe Lebesgue algebras that appear in terms of these specializations and basically not do a single argument where we compute a Poisson bracket. So this is a little bit an advertisement of how the results are proved. So that way we avoid all the reductions that appear in the Concini-Kac-Procesi work.
Milen, can I ask a question?
Absolutely.
So these Nichols algebras, they include the non-standard quantum group structures that are quantizations of,
exactly.
For example, Milen-Yakimov.
Even Milen-Yakimov you can do. Today I'm not going to do Milen-Yakimov, but I will say a little bit where exactly Milen-Yakimov could appear.
Mm-hmm.
I will say on the next 2 slides, I will say this Yetter-Drinfeld modules and Nichols algebras. And there I will say exactly where Milen-Yakimov appears. Okay, so the general result in pointed Hopf algebras is that all of them are deformations of smash products. And there are three objects that appear in this smash product. So now I want to advertise very much this area because I think it's a very, very general machinery to deal with anything that has to do with set relations. By general methods, not by case. So the first piece of data is a group G and the group algebra of the group G. The second piece of data is a Yetter-Drinfeld module for this algebra G. And the third piece of data, BV, is the Nichols algebra of this Yetter-Drinfeld module V. So to come back to Cole's question, today I'm going to consider the special case when G is an abelian group. If I take that group algebra of G and I replace it by another Hopf algebra, for instance, I can do the UQ of a levy of a parabolic, then we can recover all Belavin-Drinfeld stuff there. So if you just take that group algebra of G and replace it with the quantum group of a levy, that provides immediately all possible extensions that are needed for Belavin-Drinfeld. So now I want to define in very, very simple terms all the objects. The most understood case in this classification is the case when G is an abelian group. And for an abelian group, a Yetter-Drinfeld module is something that's super trivial. It's a G-graded G module V. So it's a module V that's direct sum of submodules, and they're indexed by the elements of the group G. So this is a Yetter-Drinfeld module over an abelian group. We say that this module is of diagonal type if the group G acts by characters on each of these modules VG. So in other words, each of them is just direct sum of one-dimensional representations. That's why it's called diagonal. So here is an example. Take G to be the free abelian group on n generators, alpha 1 through alpha n. The group algebra of free abelian group is just the algebra of Laurent polynomials. And now we fix a square matrix. So this is going to be the data that parameterizes our algebra. It's a square matrix whose entries are non-zero complex numbers. And this Yetter-Drinfeld module is just direct sum of one-dimensional representations. These are the one-dimensional representations that appeared on the previous slide. And each of the generators, Ki, acts on the corresponding vector in the representation by multiplying this by the corresponding integer Qij. So this is the simplest type, the simplest example of a Yetter-Drinfeld module of diagonal type. And it's not a difficult thing to prove that all Yetter-Drinfeld modules of diagonal type, in a sense, are obtained from this one by making the group G slightly bigger. For example, if Cij is the Cartan matrix of the Lie algebra G, and Di are the symmetrizing positive integers, then we can take Qij to be epsilon raised to that power. And that's a perfectly nice example of such matrix Q. So that's called the braiding matrix. It will appear in the next slide why it's called braiding matrix. Let's give now a super example. Let's take SLMN. We still take Qij to be symmetric, and the corresponding matrix entries are defined by these formulas. And you can, if you look at the formulas, you can easily see that behind the formula is nothing but the Dinking diagram of the Lie algebra SLMN, where we have only one odd root, which is only one isotropic odd root, and simple. Among all the simple roots that are chosen, there is only one odd that's isotropic, and the rest are even roots. So if I have a Yetter-Drinfeld module V, then this V becomes a braided vector space where we switch the order of the two elements by simply placing this complex number Qij in front. And then we can look at the tensor algebra of V, which is simply the free algebra built on the vector space V. It's a Hopf algebra in the category of braided vector spaces, some sort of free object. And just like all the time, this object, this free object, has a universal quotient that's called Nichols algebra. It's the tensor algebra that's quotiented by the maximum ideal that lives in degrees higher than 2. So this is the Nichols algebra. It's the universal maximal quotient of the tensor algebra. And because of the universality, it has many other ways of defining it. For instance, this ideal can be characterized as the kernel of some bilinear invariant form. It can be defined as the kernel of some symmetrizers that are built from sigma. So the punchline would be that this simple construction generalizes set relations in all possible situations. For example, if we do example 1, then we simply get the positive part of the small quantum group for every simple Lie algebra G. If we do example 2, we get the small quantum group corresponding to the Lie superalgebra SLMN. So all of them are simply obtained by this situation, by this construction. So now, the beauty of the story is that finite dimensional Nichols algebras are already classified. There is an extensive classification due to Heckenberger that followed earlier work of Andruskiewitsch and Schneider, who did it in a special case. And Heckenberger and Angiono were able to associate important Lie theory data to each of these Yetter-Drinfeld modules. So first of all, Heckenberger defined a root system for each of them. He furthermore defined Weyl groupoid for each of them that generalizes Weyl groups. And he defined Lustig isomorphisms between these quantum doubles of these bosonizations of a Nichols algebra, of a Yetter-Drinfeld module, the bosonization of the Nichols algebra and the group algebra. So these gadgets that are called U small, UQ here, are vast generalizations of small quantum groups. So furthermore, Angiono defined a set of Cartan roots inside the set of the roots. And the meaning of Cartan roots is that these are the analog of even root superalgebras. So in this picture, we have Cartan roots and non-Cartan roots, and these are precisely analogs, generalizations of the classical notions of even and odd roots. So furthermore, Angiono came up with an explicit description of the defining relations of the Nichols algebra BV. And these relations are complicated set relations. He has 27 different kinds of set relations, and the classical is just one of these 27. They're power relations, power Cartan roots raised to some power equal to 0, and another kind of power relations where non-Cartan roots or odd roots are equal to 0. So in this picture, Angiono defined this very important class of distinguished pre-Nichols algebras that are intermediate quotients of the tensor algebra. And they're the tensor algebra where we take away the intermediate kind of relations that are the power relations of non-Cartan roots. So just like in the case of Lie superalgebras, the positive parts of the Lie superalgebras are defined by some complicated set relations and odd roots raised to power 2 equal to 0. Similarly, for these distinguished pre-Nichols algebras, we will have the same kind of relations.
Milen?
Yeah?
I just wanted to ask, there are some odd roots, such that the square is not 0. They are Cartan roots or they are... Are they Cartan roots or not?
They're not, they are going to be Cartan roots. I agree. They're also going to be Cartan roots. So these are just exactly. That's a very important point. I was trying to just oversimplify everything. Okay, so now in this picture, I want to define a dictionary. So we're going to start with a braiding matrix Q, which is an n by n matrix with entries that are non-zero complex numbers. These are not just arbitrary square matrices. They're square matrices that come from some classification of Heckenberger of all Nichols algebras of diagonal type that are finite dimensional. Then we define the large quantum group. Here I have a typo. The large quantum group that's on line 2 is UQ without greater or equal is just U with subscript this square matrix Q. So there shouldn't be greater or equal than 0. I'll try to hide it here. So it's the Drinfeld double of this bosonization. And in a very concrete case, this recovers the big quantum groups of the Concini-Kac-Procesi. It will be called large quantum groups. In other cases, these are big quantum supergroups and so on and so forth. Inside, we have these Borel subalgebras, large quantum Borel algebras. They're the analogs of Cartan part plus the positive part of the Nichols algebra. So we're going to denote this by U greater or equal. And we have large quantum unipotent subalgebras. These are just the pre-Nichols algebras. So in this picture, we have this general machinery that puts these classes all together. And inside each of these, we have a large quantum group, large quantum Borel subalgebra, and large quantum unipotent subalgebra. For example, if we look at example 2, the super example, now I want to make this very precise. What's the relationship between our algebras and other algebras that people define? For instance, Bankart, Kac, and Kashiwara defined these quantum supergroups in the early 2000s, and related to theirs, our large quantum group doesn't have the parity element sigma. Instead, the parity element sigma is incorporated into our generators EI, FI, and KI, where some of them are multiplied by this power of this parity element, and the PI is the parity of the vertex I. It's 1 if the vertex is odd, and is equal to 0 if the vertex is even. So this is the Bankart, Kac, Kashiwara algebra, and how exactly our algebras in this concrete situation are related to their algebra. And one assumption that we're going to make is that the braiding matrix Q belongs to a one-parameter family. In other words, there is a one-parameter braiding matrix. This is going to be called boldface Q. And this boldface Q matrix is going to look like a complex number Bij times a free variable nu raised to some integral power. And the assumption is that our square matrix Q is obtained by this matrix boldface Q with the extra parameter nu by setting that extra parameter nu equal to epsilon. The meaning of this construction is that we don't look at certain algebras in the classification of Heckenberger. Those are algebras of small dimension. But at the same time, this is the basic assumption that will allow us to use specialization. Still, with this assumption, we're still covering all big quantum groups, big quantum supergroups, these Katz-Weisfeiler algebras, and others. And here is the second piece of the dictionary. I want to give you a feeling of what are our big quantum groups, large quantum groups. I still want to erase this misprint there, greater or equal. So our large quantum groups are going to have the Chevalley generators EI, FI, and the Cartan generators KI and LI. So we have two copies of the Cartan generators because all the time we're taking the Drinfeld double here. And because we take the Drinfeld double, we have two copies of the Cartan subalgebra. As you know very well, the second copy of the Cartan subalgebra is no big deal because we can quotient by some central elements. So this is not really changing the picture in any way. So the relations in this algebra are like the usual relations for a quantum group, except that we will never write down the set relations on E and F because they're extremely complicated. So we have the usual relations between E, F, K, and L. We still have the Cartan roots raised to some power equal to 0. But we're not going to record these set relations which come in many different flavors. We will just work abstractly with the algebra, avoiding any direct calculations with them. And in this generality, one can define root vectors for our algebra. So we do have a PBW basis of the positive and negative part. Again, it's done in terms of the of the root vectors E beta and F beta, but for the non-Cartan roots, certain powers of those will be equal to 0. So that would be part of our algebra. Like in the quantum SLMN, in the super case, one of the generators squared is equal to 0. So now I want to finish with the results that I want to report on. So the first part is that each large quantum group is a specialization of a non-restricted integral form of a certain quantum group UQ, where Q is this matrix that has the extra parameter mu. So this immediately makes the pair UQ and the center of UQ a Poisson order. And again, a special case, we have a result like this for all quantum supergroups, big quantum supergroups. Now, this center is very singular, so we definitely don't want to do any Poisson geometry with that singular part. There are a number of results that deal with the singularities in general in the literature, but when you really use the Poisson geometry, you don't really want to deal with that singular center. Now, if you look at this subalgebra ZQ, the one that's written over here, is the algebra generated by the n powers of the Cartan roots, E and F, as well as the, this power should be n beta everywhere. I'm sorry, this beta beta should be n beta, that's typo. So this beta everywhere should be n beta. So this subalgebra was previously defined by Angiono, and he proved that this subalgebra is inside the center, and it's a Hopf subalgebra of the center. So the second part of the theorem is that it is actually invariant under the Lustig isomorphisms, and UQ is module finite over it. That's the second part. And the third part, this is the most challenging part here, is that the central subalgebra is a Poisson subalgebra of the full center of the large quantum group. So that immediately implies that the pair UQ-ZQ is a Poisson order. So we're going to do geometry with this Poisson order. And I want to say where the parts of the theorem here compare to the Concini-Kac-Procesi. So in the Concini-Kac-Procesi, this third part, that ZQ is a Poisson subalgebra of the full center, is proved by rather direct methods using explicitly the Poisson structures. Again, we couldn't do this in our situation because it's too complicated to deal with so many set relations. It's just impossible to handle simultaneously 13 different kinds of new set relations. So the punchline for the difficult part is the following. We prove that this ZQ plus, which is the intersection of ZQ with UQ plus, is actually precisely the fixed subalgebra of the full center under a set of skew derivations, which actually descend for the quantum group with parameter mu. So we have now an invariant definition of this special central subalgebra. It's not just the subalgebra generated by something, but it's precisely the fixed points of the full center under something. And then we prove a general theorem that every time you have something that's fixed under a set of skew derivations, and you have a Poisson structure on the full center that comes from specialization, then this fixed subalgebra, fixed point subalgebra, will automatically be a Poisson subalgebra. So by running this general argument on the bottom of the slide, we avoid any concrete calculation with the central subalgebra and Poisson brackets. We simply have a general result that can be applied in other situations too. So this is the first theorem. The second part now is let's look at these Poisson orders and let's see what we can say about the Poisson Lie groups that are involved. So we have two kinds of Poisson orders. One is the large quantum group, and the second is the large quantum Borels. And in the paper, we also have the large unipotent groups, which I skipped from the top. So here we know that the center ZQ and ZQ greater or equal than 0 are Poisson-Hopf algebras. Just like I mentioned, Cole used this in a very essential way to study the tensor products of representations. Now, since they are Poisson-Hopf algebras, the corresponding, the spectra of these Poisson-Hopf algebras, we're going to call those MQ and MQ greater or equal than 0, are going to be Poisson algebraic groups. And also from general nonsense, we know that these connected Poisson algebraic groups are, these Poisson algebraic groups are actually connected. So now we're down to the problem, how can we describe these Poissonic groups, provided that they're connected? And it's very well known in this theory that all you need to know is to describe the tangent Lie algebra, and then you will use the connectedness in order to get immediately what's the Poisson structure. So this is the part where the Concini-Kac and Procesi used a lot of direct calculations, and we go around all of it by a general set of arguments. So the first part is that if you have any large quantum group, the spectrum MQ of ZQ is simply a product of two Borel subgroups of a certain semi-simple algebraic group GQ of adjoint type. And the second part is that the spectrum of this subalgebra of the Borel ZQ greater or equal than 0 is precisely the Borel subgroup of this group GQ. One can say very explicitly that this group GQ has root system that's precisely coming from the set of Cartan roots of our large quantum group. For instance, if we're in a case SLMN, this GQ would be precisely the even part. And this is the first thing that just described this as algebraic groups. And the second part that describes the Poisson structures is that the Poisson structures on these groups are precisely, so these are precisely the dual Poisson-Lie groups to the groups GQ and DQ minus, where GQ and DQ minus are equipped with Poisson structures from the Belavin-Drinfeld classification, but where the Belavin-Drinfeld triple is trivial. So to come back to the very early question of Kohler, we still have everywhere Poisson structures that have empty Belavin-Drinfeld triples. And in order to get non-empty Belavin-Drinfeld triples, we have to consider even more general quantum groups than the ones that appear here.
Milen, sorry, what do you mean exactly by empty Belavin-Drinfeld triple?
So the Belavin-Drinfeld triple consists of subsets of the Dinking graph and isomorphism. Both sets are trivial.
Okay.
So these are the Belavin-Drinfeld structures that appeared once in a paper that you wrote in Letters in Mathematical Physics.
It's twisted by Cartan.
Twisted by Cartan, precisely. So in Kohler's language, these are Poisson structures that are twisted by Cartan. So the key argument here, really the big part of the work, is how to prove this part 2 of the theorem. And it's done without any direct calculations of Poisson brackets in any reductions to low-rank cases. Just like I said, the Concini-Kac-Procesi at some point say, in order to describe the underlying Poisson group, we're just going to look at all possible Poisson brackets coming from generators that satisfy Serre relation. And the Serre relations for the usual groups have just two generators, and these are the usual Serre relations. So they have several pages of arguments with the usual Serre relations. However, when you look at the list of relations that Ivan Angiono produced for all these algebras, there are 13 different kinds of Serre relations. So if you have time, at the end, I will show all the different kinds of Serre relations. For the algebras, even just the super algebras, there are like 13 different kinds of Serre relations. And altogether, we have Serre relations up to 4 generators. So this is practically impossible to follow the idea of the Concini-Kac-Procesi, because there will be too many cases, and some of the cases will be humongous, because even in the case of 2 generators, they have a very long sequence of arguments to compute Poisson brackets. So in a nutshell, we do the following. Inside each of this quantum group that has the extra parameter Q, we have both a restricted and a non-restricted integral forms. The restricted integral forms has the divided powers, and the non-restricted integral form has no divided powers. And then there is a natural perfect pairing between these algebras. And the algebra A here that defines the integral forms is something like Laurent polynomials in this extra variable nu. So from the pairing, we're able to prove that if you look at the dual tangent Libby algebra of MQ greater or equal than 0, we can completely define this intrinsically in terms of these restricted integral forms. So previously in the work of the Concini-Kac-Procesi, you everywhere see the non-restricted form. So the moral here, the beauty of the story is that we want to say, no, actually the restricted plays a very major role when you define intrinsically, describe intrinsically the dual tangent Libby algebra is done intrinsically in terms of this restricted integral form. And then from here, you can prove that this just a direct argument coupled with previous results of Ivan and Nicolas that, sorry about this. So from these results, you can prove that the tangent Libby algebra is precisely the Lie algebra of this Borel subalgebra BQ minus. So this proves the result for the Borel part. And then we use Lie theory in order to prove that the dual Lie tangent Libby algebra of the whole MQ. So the previous result here was about MQ greater or equal than 0, because we use dual pairings between and negative parts and not for the whole quantum group. So this first part here, in terms of restricted forms, it only handles this Poisson Lie group MQ greater or equal than 0. And it proves that its tangent Libby algebra is the Borel subalgebra. Let me try to get this thing now. I just want to get the controls out. They don't want to come out. Oh, super. So then when we work with the dual tangent Libby algebra, we can use some Lie theory arguments in order to cook together the two Borel subalgebras to prove that this dual tangent Libby algebra is precisely the Lie algebra of GQ. And finally, the product of the two Borels is identified with a subset of GQ times a torus. It is not the maximal torus of GQ, it's more complicated than that. And the first result is that the symplectic leaves of this MQ, that's the spectrum of the central subalgebra of the large quantum group, so the symplectic leaves are in bijection with conjugacy classes of GQ times the points of this extra torus. So the algebras, these fiber algebras UQ mod MUQ are isomorphic to each other across conjugacy classes. And then in the case of large quantum Borels, there is a torus that acts on MQ greater or equal by Poisson automorphisms. And the fact here is that the statement here is that the torus orbits of symplectic leaves of MQ greater or equal than 0, then greater or equal, are in bijections with double Brucha cells. In particular, they're finitely many. And then the corresponding algebras are just finitely many, and they're parameterized by the Weil group elements W. So altogether, the first part of the theorem describes invariance of these fiber algebras along conjugacy classes. And in the second part, we have invariance of these fiber algebras along finitely many double Brucha cells. So the final result is somehow exactly the same as the classical results, but the key point is that the way these results were obtained here is quite different now from the classical situation, because that is really cannot be extended per case. I personally doubt that even in the case of SLMN, one can do a case-by-case construction on the set relations. So that's going to be all, and thank you so much for the invitation again.
Thank you. So, questions?
I think you definitely said this before, but what's the difference? Why is one large and one big?
So we didn't want to use, it's a great question. we didn't want to use the same term because the term big quantum group is already taken. And we just wanted to come up with a new term. It's not that these large are bigger than the big ones. It's just a much bigger class that contains other subclasses. So we just wanted to have a term for that class. And we thought, hey, let's do large. Nobody has picked up large.
Thanks.
More questions? Yes.
Milen, could you explain about this torus?
Great. Thank you, Vera. So there are these slightly non-standard Poisson structures that appear over here. And when these non-standard Poisson structures appear here, we have to see how exactly the algebras are embedded in the corresponding double. So whatever appears over here, that BQ plus times BQ minus is identified with a subset here, what really we're doing is we're embedding BQ plus, BQ minus inside some double in a particular way and quotient the double by some diagonal of G. Because that double is not the standard one, when we do this projection, we're going here something that's not really a torus. I'm even cheating more. It is the space C that's quotient by one lattice plus another lattice. And when we do this addition of one lattice plus another lattice, in the standard case, it happens that the second lattice is minus the first. So when you do lattice A plus minus lattice A as a lattice, that's still A, and you get the torus. Here, we're forced to do a lattice plus another lattice, but they're sort of not talking to each other anymore. And when we take this affine space and we quotient it by this finitely generated abelian group, we get something that's not even a Lie group. So what I'm calling here a torus is something that simply comes from this slightly non-standard Poisson structures like Cole said, the Cartan twisted, twist by Cartans. And from this Cartan of twist of Cartan, this is just, it's like C to the n quotient by a lattice of order n plus a lattice of order n.
Milen, and what can you say about the braiding in this case?
It's a all great question. So right now we are working on coming up with the second part of the story that these guys should be maximal orders. This is very important because then we can have trace map and all kinds of things. However, the difficulty is that in some situations, these algebras are not prime, but semi-prime. So prime is an algebra that looks like a matrix algebra, and one can apply non-commutative algebra to deal with these things very efficiently. But these algebras are not semi-prime. These are not prime sometimes, so the story gets more complicated. So things like what is the braiding, what's the tensor product of the representations, what we can say about representations using this theory of Cayley-Hamilton algebras of Procesi. So these are things that are very interesting, but we're still very far from knowing any of them.
Okay, thank you.
Definitely, we hope that this representation theory could be of some interest. For instance, the quantum SLM and the quantum super SL could be of interest to some other areas, not just in terms of the algebra itself.
Okay. Any more questions? Okay, so let's thank Milen again, and thank you very much for the great talk.
Thank you so much again for the invitation. I'm very grateful to you, Vera and Kola, for this invitation. So it was a great practice for me to prepare this and also to advertise the results.
Thank you.
How do you put this yellow hands?
It's reactions. Yeah.
Reaction.
Like this.
But how to raise a hand, by the way? I don't know.
Oh, you go to participant list and there is a blue button.
Ah,
Oh, there are blue hands.
yeah, okay.
Yeah, it's a different kind of hand.
Okay.
And Vera, I just saw right now that you asked whether H is central. So that's the
Yeah, it's okay. Sasha answered it immediately. So it's okay.
The moment I was reading this on the slide, I saw that it was not
Yeah.
there.
Well, Milen, thanks for coming.
Thank you so
Thank
much.
you. Thank you very
I
much.
hope that
We hope to see you live sometime soon.
okay. Hope the weather gets better in Berkeley.
Yes, we too.
Okay. Thank you so much again.
Okay.
Bye.
Bye.